part of a kinetics FRQ question. It's a pretty challenging one. We've got nitrogen monoxide reacting with bromine to make some nitrosyl bromide. They give you an instantaneous reaction rate table where you're given specific concentrations and exactly what happens in terms of how quickly the NOBr is being produced at that specific set of concentrations, its rate. As you can see on the first one, 16 millimolar nitrogen monoxide and 12 millimolar bromine, our reaction rate where we're getting our NOBr is 3.24 times 10 to the negative 4 molar per second. So we're getting that product that quickly, and we have the same sort of changes that we see when we have different concentrations of nitrogen monoxide and different concentrations of bromine. With these instantaneous rate problems, you've got a lot of numbers that you've got to compare, and one of the best things to do is to try and simplify things just a touch so that you're not distracted by the numbers. So what I've done is round this off so that you can look at the numbers and see the patterns more easily. Let's look at these new patterns. So here I've rounded the initial rate of appearance down to two significant figures, the 3.2, 6.3. Probably should have rounded off to 6.4 and 6.4. The second experiment, though, isn't going to be irrelevant because I'm interested in determining the order of the reaction with respect to NO. I need a comparison where the NO is being changed, and the only time that happens is between experiments 1 and 3, where I have some data for the rate of the reaction. I'm going to get rid of the second experiment because I don't want it to distract me. With that second experiment eliminated, you can see we're just going to compare experiment 1 to 3, where our concentration of NO is doubled. But there's a problem because the bromine is also changed. Now, typically, when you want to find out what's happening with the nitrogen monoxide, you don't want also to have the bromine interfering with it. And the bromine there is down in terms of having its concentration decrease. So we've got a problem there. Fortunately, we know that bromine has an effect on this reaction as being first order. So we can change that from 0.006 and increase it to figure out what it would be if it had not changed. We're going to double that concentration of bromine so that there's no change between experiment 1 and experiment 3. But of course, that means our rate of appearance is going to have to be changed too. Change that concentration of bromine to twice what it should be. And of course, that will mean that the rate of appearance of NOBr will be twice that too, because bromine is going to change the rates of reaction according to the first order. So we've in effect decided that the bromine NOBr appearance is going to be 12.8 times 10 to the negative 4, double what it was when it was 0.006. And that makes sense. Now this is going to set things up very nicely because now experiments 1 and 3 are set up so that the bromine has the same concentration. Now we can compare the concentration of NO change. Well, it's double, 0.016 to 0.032. The concentration of the NO is increased by a factor of 2. Well, what happened to the rate of the reaction? Let's compare that. Well, it goes from 3.2 to 12.8. That's an easy one to figure out. That's going to be 4 times the reaction rate. So when we double the concentration of NO, rather than doubling the rate of the reaction, we make it 4 times greater, which means that the NO must be second order. It's going to change the reaction by its square. It's going to be more important than the bromine is. If you triple the NO, you'd expect the rate of appearance of nitrosyl bromide to be 9 times as much because it's that by second order. So we've answered the question, determining the order of the reaction with respect to the nitrogen monoxide. Now we've got to explain our reasoning. Now you could, going through this in terms of saying that you realize that doubling the concentration of the NO increases the rate of reaction by a factor of 4. Another way of doing this, though, is to prove that this rate law is correct based on the equation. And that's what I'm going to do. We have a rate constant. And if our equation is correct, that rate constant will be a constant. So let's calculate the rate constant for this reaction using the data for trial 1. So trial 1 had a rate of 3.2 times 10 to the negative 4, typing in my calculator. And to calculate the constant, I'll divide by the concentration of the NO, 0.016 second order squared. And there we go, I got my squared. And then also divide by the concentration of the bromine to the first order. Both of those are going to end up giving us our final K, our reaction rate constant, which is 104. So based on this rate law, K is 104. Now, one of the things that we should be very careful about is when you calculate the rate constant, you have to be very careful about the units. And I wanted to talk about the units right now because they're usually worth 1 point on an exam. So the rate will always be a concentration per second or per hour. So we have to set things up so that 104 times our data will produce concentration per second, in this case molar per second. Well, the NO is molar squared, the bromine is molar. So in order to get our final answer in terms of meters per second, that 104 has to have meters per second in the denominator to cancel out things so that in the end, we end up getting molar per second. Our constant has to have, because it's, in this case, overall reaction third order in terms of per molar squared and second. So there we got it figured out. Well, that's our constant with the correct units. Now let's see if it works. Let's try this now with trial 3. Now trial 3 has a rate of 6.4 times 10 to the negative 4 molar per second. We're going to divide that by the initial concentration of the NO, which is 0.032, which we're going to square, of course. And then we're going to divide that by the bromine, which is the 0.006, and see what number we get. If we're right, we'll have the same constant. Let's see. Let's put that entry in, and ding! Here we've got our answer, 104. So this rate law is correct. We've explained that this is the only combination that we'll have that will be valid for this reaction. So we can figure out this reaction anytime. If you know the concentration of the nitrogen monoxide and the bromine, you can find out how fast this reaction is going at that instant. This is the proof that this is the correct rate law for this reaction. Of course, this was all about instantaneous rates. Now, there's another way of looking at reactions, and that's to see what happens to them over time. So we've got our time here, and we can view the concentrations over time. In this case, where we've got 1 molar bromine and 1 molar NO, and we keep the NO at 1 molar, that bromine concentration will decrease. And notice this is pretty fast. Within a blink of an eye, less than a second, our concentration goes from 1 molar bromine down to virtually 0. This type of graph can also tell you the order of the reaction with respect to the elements. If we keep the NO concentration as 1, this is what happens as our bromine. That'll be tough to do. But of course, a curved graph is very difficult to explain and figure out. How can we find what's going on easily with this? Because it keeps on changing. There's another way of analyzing this. And we're going to flip this down, and instead of plotting the concentration versus the time, we're going to switch over to another method. This is where we're going to plot the natural log of the bromine concentration. Of course, the natural log, you get your 2.718 raised to the power, and that power, of course, in this case is what the natural log is. And indeed, when we plot this, we get ourselves a beautiful straight line. When we plot a first order reaction, we get a straight line because the logarithms take care of this gradual change. We had 104 for the slope of that line. Now let's look at our nitrogen monoxide, which we found out was second order, and see if it really does. Now this takes an even greater plunge. We'll look at this within a 0.05 of a second, a blink of an eye, the concentration drops from 1 to less than 0.02. So this reaction is going gangbusters at first. And then, of course, with a lower concentration of NO, we're keeping the bromine at 1 molar, we end up having our reaction slow down. So it drops quickly, and then it sort of slowly graduates down. Well, let's see if a natural log plot will help us with this. So we'll do the same thing we did with the bromine, and we'll try plotting again. The curve is smoothed out a little bit because of the logarithmic relationship, but it's not a straight line. This is because a second order rate of reaction order is not going to plot out a straight line with a natural log. We're going to have to use another integration. That other integration is plotting 1 over the concentration of the NO. And look at this. When we plot 1 over the NO, we get that beautiful straight line, and the slope is 104, which just happens to be the rate constant. So this is another way of identifying the order of a reaction. If it plots out with 1 over NO as being a straight line, you know without doubt it's a second order reaction. Well, that was a lot of work, but it explained a lot of kinetics. Here's our summary. First order reactions plot out beautifully. The negative of the slope is the rate constant, and the second order reactions straighten out when you have 1 over A. Now let's look at our nitrogen monoxide. It's a really unusual gas. Nitrogen monoxide is colorless. Our NO2 has a definite brown color to it. And here you can see that reaction done by Peter Werthers at the Royal Society of Chemistry doing his nitrogen,
a gas called nitrogen monoxide.
But
But this is colorless. The gas jar here, I've put a white card in this to help us see it, but the gas jar contains nitrogen monoxide. Now, this gas jar just contains air, but when the nitrogen monoxide reacts with more oxygen, so nitrogen monoxide plus more oxygen, forms another gas called nitrogen dioxide, and this is actually a brown color. As soon as the two gases mix, the brown color is formed due to the nitrogen dioxide.
nitrogen monoxide, also called nitric oxide, is also used in a famous demonstration called the barking dog demonstration, where it's been used for the past 150 years to entertain audiences. Here's Peter Werthers doing the same.
Inside the tube here, there's a gas called nitric oxide. This is a colorless gas, but when we take the top off of this, you may well see a brown gas coming out, and this is due to the reaction with the nitric oxide reacting with the oxygen in the air, forming a brown gas called nitrogen dioxide. Well, I'm going to add some carbon disulfide to this. So we're mixing these two reagents together, and in a moment we're going to apply a light to the top, and you should see some light forming. Okay, thank you. Just in case you missed that one, we'll try a slightly bigger one. The nitric oxide, NO, and the carbon disulfide. If we have the lights down, please.